When you send electromagnetic waves at a target, those waves bounce back. The bigger the target, the stronger the return signal. A square meter of flat metal hit by radar at 10 gigahertz produces a radar cross-section of nearly 14,000 square meters. That's the physics. You can't argue with it. So at least theoretically, a bomber the size of the B-21 with an estimated 140-foot wingspan should light up radar screens like a billboard. Yet this aircraft cannot be tracked by even some of the most advanced air defense systems ever built. Here's why. Start with shape. When a radar wave hits a conventional aircraft with a rounded fuselage and protruding engines, strong radar energy reflects back toward the radar. That means the aircraft appears big on a radar screen. That's the opposite of stealth. The B-21 was designed to reduce how much radar energy gets reflected back. Instead of simple curves and exposed components, the B-21's flying wing shape uses smooth, blended surfaces that are aligned, so radar waves are directed away from the source rather than directly back. This lowers the strength of the radar signal that returns to a radar receiver. One of the strongest radar reflection points on any jet aircraft is the engine's fan face. The spinning metal blades inside behave pretty much like rotating reflectors. If radar waves travel straight down an intake and strike those blades, the return signal increases dramatically, and there is no stopping it. To prevent this, the B-21's engine inlets are positioned closer to the center line rather than hanging under the wing. The intake ducts are shaped so that radar waves cannot travel in a straight line to the fan blades. Other stealth aircraft use similar S-shaped ducting for this exact reason. And while the precise geometry of the B-21 remains classified, the principle is consistent with established stealth engineering practice. Radar-absorbent materials, or RAM, are what most people think of when they hear stealth. The B-21 uses next-generation RAM that's leagues beyond what the B-2 had. The latter's coatings, for those unaware, were notoriously finicky. They required constant maintenance, frequent reapplication, and were sensitive to weather. The B-21, on the other hand, was designed from day one with sustainment in mind. So how do these materials even work? When a radar wave hits a surface, RAM reduces its reflection by converting some of the electromagnetic energy into heat. This happens through magnetic and dielectric losses inside specially engineered materials. Earlier generations often used ferrite particles or iron-based compounds suspended in polymers. These materials interact with the incoming electromagnetic field and dissipate energy instead of allowing it to reflect cleanly. Modern stealth designs do not rely on a single material. They often use layered systems. Each layer is engineered to match the impedance between air and the aircraft's surface, which reduces reflections. Different layers can be tuned to different wavelength ranges. Since modern radar systems operate across multiple frequency bands, stealth coatings must work across a broad spectrum. Some advanced materials in the wider aerospace industry use carbon-based composites or conductive polymers to enhance absorption. While the exact composition of the B-21's materials remains classified, it likely benefits from decades of material science progress since the B-2 was designed. Now, it's time for integration. Instead of applying fragile stealth tiles or thick external coatings, modern aircraft increasingly incorporate absorbing properties directly into composite skins. This reduces maintenance demands and improves durability. The B-21 was designed using modern digital engineering and advanced composite manufacturing, which likely allows stealth treatments to be built into the structure itself rather than layered on top afterward. Alright, we've explained how the B-21's shaping and materials work against traditional radar, but adversaries are not standing still. Stealth technology was originally optimized for higher frequency radar systems, the kind most common air defense radars use. Those operate in centimeter wave bands, where careful shaping and coatings can dramatically reduce the strength of reflected radar energy. But there are other kinds of radar out there. Low-frequency radars operate in the VHF and UHF bands, which have much longer wavelengths. When a radar wavelength becomes comparable to the size of the aircraft, some of the stealth reduction techniques become less effective. Stealth aircraft generally appear bigger to these long waves because the physics of scattering works differently. Radar designers have known this for decades, and low-frequency systems were even used to detect the F-117 during the Kosovo War, precisely because of this effect. But low-frequency radar comes with trade-offs. Because of their long wavelengths and wide beam widths, these systems cannot pinpoint precise location, range, and altitude as modern high-frequency radars can. On their own, they often can tell you something is out there, but not exactly where it is or how to engage it effectively. This is why modern sensor networks don't rely on a single type of radar. They combine different systems to try to compensate for each other's weaknesses. A low-frequency system might offer early warning, but higher frequency systems, infrared sensors, and tracking radars are needed to create a full targeting picture. There are also emerging technologies that theoreticians and researchers discuss when talking about the future of detection. One of these is quantum radar, which aims to use quantum mechanical correlations between photons to detect objects that conventional radar might miss. In theory, quantum sensing could overcome some stealth advantages because it relies on fundamental quantum effects rather than simple reflected energy. But quantum radar technology is still experimental and faces enormous challenges before it can be deployed operationally at long ranges outside of laboratory conditions. Another key reason the B-21 Raider is different from older stealth aircraft is its modern mission systems design. Earlier platforms, including the B-2, were built with avionics and mission computers that were state-of-the-art at the time. But that architecture made upgrades difficult and slow. When new sensors, electronic warfare systems, communications gear, or software capabilities became available, integrating them often required long, expensive overhauls. With the B-21, the U.S. Air Force and Northrop Grumman intentionally took a different path from the very beginning. They built the bomber around an open systems architecture. This means the underlying software and hardware interfaces use standardized protocols and modular connections. Engineers can add new mission systems without interfering with the aircraft's core flight functions. Because of this modular structure, updates to radar warning receivers, electronic attack tools, communications gear, or target identification systems can be made much more quickly than in older designs. You can think of it as a platform where components plug in easily, rather than being baked into the airframe's core software. This approach reduces what defense planners call integration risk. So does this make the B-21 invincible? No. No aircraft is immune to detection or attack. Stealth does not erase physics, and it does not guarantee survival in every scenario. What it does is change timing and probability. Low observability reduces detection range. When the detection range shrinks, everything else in the engagement chain gets compressed. Radar systems have less time to confirm a track. Command centers have less time to classify the contact. Missile batteries have less time to calculate firing solutions. Interceptors have less time to scramble and position. But this is not the only upper hand this craft offers. The Northrop Grumman B-2 Spirit is often cited at around $2 billion per aircraft when development costs are included, making it one of the most expensive aircraft ever produced. The United States Air Force did not want the same outcome with the B-21. Rather than building a few very expensive bombers, the Air Force and Northrop Grumman aimed to produce a larger fleet with better long-term affordability and maintainability. Public estimates put the average procurement unit cost of the B-21 in the range of roughly $550 million in 2010 dollars, which, when adjusted for inflation in recent years, is around $700+ million per aircraft, if based on at least 100 aircraft production. This figure includes procurement funding and support equipment, not just the bare airframe. However, cheap doesn't necessarily mean compromise. The U.S. Air Force describes it as a dual-capable penetrating strike bomber that can deliver both conventional and nuclear munitions. This does not mean the B-21 is a one-trick platform carrying only gravity bombs. It is designed to be interoperable with a broad array of weapons. Public reporting indicates it is planned to be able to carry both traditional gravity weapons and standoff weapons, including extended range missiles such as variants of the AGM-158 family. While some details of planned weapon loads are still classified or evolving, the concept of a flexible payload mix is officially recognized. Range is yet another important operational strength. While exact performance figures remain classified, analysts and defense researchers estimate that the bomber will be capable of flying around 6,000 miles or more without aerial refueling. That means the Raider could take off from a secure base in friendly territory, reach distant targets deep inside an adversary's airspace, complete its mission, and return without needing to rendezvous with tanker aircraft over dangerous regions. This is why the US Air Force has committed to acquiring at least 100 B-21 Raiders, though senior military leaders and defense analysts have publicly discussed arguments for increasing that number. Within official planning documents and force structure discussions, the Raider is positioned to incrementally replace the aging B-1 Lancer and B-2 Spirit bombers as those platforms reach the end of their useful service lives. The B-21 is also integrated into broader bomber force planning alongside modernized B-52 Stratofortress aircraft, creating a mix of penetrating strike and long-range deterrent capabilities for decades. And while many might not know about it, the development timeline for the B-21 Raider also stands out in modern military aviation. The concept for a new long-range strike bomber emerged with the Long Range Strike Bomber (LRSB) program in 2011, and the contract to design and build the aircraft was awarded to Northrop Grumman in 2015. This marked the start of a focused effort to field a next-generation bomber capable of operating in environments where advanced integrated air defenses could challenge legacy platforms. The first public unveiling of a B-21 airframe took place in December 2022, and the aircraft then completed its first flight in November 2023. Following that initial milestone, additional prototypes and test aircraft have continued joining the flight test program through 2024 and into 2025, expanding the scope of testing to include mission systems, mission data integration, and weapon system checks. If you enjoyed this video and want more breakdowns that go beyond headlines and into the real engineering behind military tech, hit like and subscribe. Thanks for watching. I'll see you in the next one.